Alright, let's have a look at some of the questions in homework of topic 10. Okay, question number 2. In triangle ABC, AC equals 17, BC equals 27. For how many integer values of AC is triangle ABC acute? So in this case, we can let A equals BC, which is 27, and B equals AC, and C equals AB. In this case, that's 17. The triangle ABC is acute. If and only if, you could use this sign here, or you could also use IFF, if and only if. A squared plus B squared is greater than C squared. A squared plus C squared is greater than B squared, and B squared plus C squared is greater than A squared, right? So the first inequality becomes 27 squared plus B squared is greater than 17 squared, right? Or we could simplify that to B squared is greater than 17 squared minus 27 squared, which is negative 440, which is automatically satisfied. So we don't really care about the first one, right? The second inequality is equivalent to 27 squared plus 17 squared must be greater than B squared, right? And this can be simplified to B squared must be less than 17 squared plus 27 squared, which is 10, 18, right? This is satisfied by B equals from 1 to 31, right? Because if B equals 32, that is B squared is greater than this number then. So this means B equals 1, 2, or 3, all the way until 31, right? And then let's consider the third inequality here. Third one is equivalent to B squared plus 17 squared must be greater than 27 squared. And we can simplify this to B squared is greater than 27 squared minus 17 squared, which is 440, right? This is satisfied by B is greater than or equal to 21, right? Therefore, triangle ABC is acute. We can make this conclusion here. Triangle ABC is acute for B equals 21, 22, all the way until 31 for these numbers, which consist of 11 values. So the correct number of the solution is 11 here. Okay, have a look at the solution here and let me know if you have any questions, okay? Alright, if no questions, let's have a look at the next one. Okay, number 3. Lengths of two sides of triangle are 7 and 3 centimeters respectively. If the number of centimeters in the perimeter is a whole number, what is the number of centimeters in the positive difference between the greatest and least possible parameters? So first of all, due to the triangle inequality, the third side must be less than the sum of the other two sides, which is 7 plus 3, which is 10, right? Therefore, the largest the third side can be is 9 centimeters. If we let the third side of the triangle be x, in order to facilitate our discussion, let the third side be x. Of course, the unit is centimeters. So we must have x plus 3 is greater than 7. So this gives us x must be greater than 4, right? Therefore, we know the smallest the third side can be is 5 centimeters. Then the greatest possible parameter is 3 plus 7 plus 9, which is 19, right? So we have, well, let's say parameter. Well, let's say max parameter is 3 plus 7 plus 9, which is 19. And the least parameter is, which is the minimum, which is 3 plus 7 plus 5, which is 15, right? And their difference must be 19 minus 15, which is 4 centimeters, right? So the correct result is 4 centimeters. Okay, again, have a look at the solution here. Let me know if you have any questions, all right? Alright, if no questions, let's have a look at question number 4. So, ABCD is a square and O is a point. Prove that distance from O to A is no greater than the sum of the differences from O to the other 3 vertices, no matter which point we take to be point O. So suppose we have a square ABCD here. And if you actually choose any, well, if you choose O here, apparently AO is 0, and OBOC plus OD is not 0. In that case, this is always true, right? So we don't consider this case here. This is obvious. And if O is not on top of A, then suppose, let's say, O is here. And in that case, from triangle ACO, we have AC plus CO is greater than AO, right? And in triangle BDO, which is the angle here, we have BO plus DO is greater than BD, right? So adding these two inequalities gives us AC plus CO plus BO plus DO must be greater than AO plus BD, right? Because ABCD is a square, we have AC equals BD, right? So we can cancel AC and BD in both sides. And this gives us BO plus CO plus DO is greater than AO, right? So we can prove this statement is actually true. Of course, if O is on top of either B, C, or D, the statement here is obviously true. So I'm not gonna write the cases where O is on top B, C, or D there. Okay, we only consider general cases where O is not on top of A, B, C, or D. Okay, have a look at the solution here, and let me know if you have any questions. Okay.
What if point O is outside square ABCD?
Alright, if no questions, let's have a look at the next one. Question number 11. As shown below, Q is on PR and circles P, Q, and R are drawn such that no two circles intersect and no one circle contains the other two. Suppose a fourth angle can be constructed that is externally tangent to all three of these circles. A uses triangle inequality to prove that the radius of our fourth circle is greater than the radius of circle Q. Okay, let's solve the first one here. We could let okay, so letter O is not used, so we can let circle O be the circle that is externally tangent to the given 3 circles. Also, we could let the radii of the 4 circles radii is a plural form of radius. Circle O, circle P, circle Q, and circle R, B, R, O, R, P, R, Q, and R, R respectively, right? So as we learned in the previous lesson, if 2 circles are externally tangent, then the point of tangency and the centers of the 2 circles are all collinear, right? Therefore, the distance between the centers of these circles is the sum of the radii of the 2 circles, right? So, applying the triangle inequality to triangle OPR, we have OP plus OR greater than PR, right? So we have RO plus RP, that's OP, right? Plus OR is RO plus RR, right? That must be greater than PR. Since our given circles do not intersect, we have PR must be greater than RP plus RR plus 2RQ, right? And therefore we have RO plus RP then plus RO plus RR must be greater than PR, and PR is greater than RP plus RR plus R 2RQ, right? And simplify this gives us 2RO is greater than 2RQ, right? Because we can cancel RP, RR here. That means 2RO is greater than 2RQ. And eventually we can prove RO is greater than RQ, right? As desired. Okay, and for the second question, we can define circle O and RO, RP, RQ, and RR as in the previous part. And then either angle OQR or OQP must be at least 90 degrees. Right? Suppose without loss of generosity. Alright, suppose without loss of generality that angle OQR is greater than or equal to 90 degrees, then we have segment OR must be the longest side of triangle OQR, right? Therefore, we have OR must be greater than QR. And therefore, we have RO plus RR must be greater than QR, right? And since circle Q and R don't intersect, we then have QR must be greater than RQ plus RR, right? Therefore, we have RO plus RR is greater than QR, which is greater than RQ plus RR, right? And eventually that gives us the desired inequality. We have RO is greater than RQ. Alright, have a look at the solution here and let me know if you have any questions. Okay, if no questions, let's have a look at the next one. Okay, A, B, C are three positive real numbers such that a squared plus b squared is greater than c squared, a squared plus c squared is greater than b squared, and b squared plus c squared is greater than a squared. Prove that a, b, and c can be the lengths of the sides of a triangle. So, as long as we can prove a plus b is greater than c, and a plus c is greater than b, and b plus c is greater than a, then ABC can be the lengths of the three sides of a triangle, right? Okay, so let's start from a plus b. So we are given squared a and b, so let's take the square of a plus b. So a plus b squared equals a squared plus b squared plus 2ab, right? And apparently that is greater than a squared plus b squared because a and b are three positive real numbers, right? And it's also given that a squared plus b squared is greater than c squared. Therefore, we have a plus b squared is greater than c squared because they are positive real numbers, so we can safely take the square root of both sides of the inequality. So this gives us a plus b must be greater than c, right? Similarly, a plus c squared is a squared plus c squared plus 2ac, which is greater than a squared plus c squared. And according to given information, this is greater than b squared. And again, we take the square root of both sides of inequality. This gives us a plus c is greater than b, right? And using the same method, we can also prove that b plus c squared equals b squared plus c squared plus 2bc. And this is greater than b squared plus c squared, which is greater than a squared. Then square rooted both sides of the inequalities. This gives us b plus c is greater than a, right? Therefore, we can prove that a, b, and c are or can be the length of the sides of triangle. You get it? Alright, if no questions, let's consider last one. Question number 13 proves that distance between any 2 points inside triangle ABC is no greater than half of the parameter of triangle ABC. So first of all, let's draw a triangle ABC. It could be any triangle, right? Let's suppose this is our triangle ABC. And we have some arbitrary points PQ inside triangle ABC. Okay, so we can let P and Q be the 2 points inside triangle, and actually we can extend PQ. Let's say extend PQ to the size of triangle ABC at points. Let's call them P prime and Q prime here. So without loss of generality, we can assume P prime is on side AB and Q prime on AC. Clearly, we have PQ must be less than or equal to P prime Q prime, right? So applying the triangle inequality to this triangle, P prime B Q prime, we have P prime Q prime connect these 2 points. We have P prime Q prime is less than or equal to P prime B plus B Q prime, right? And similarly, we have in triangle BQ prime C. So BQ prime C we have BC plus Q prime C is greater than or equal to BQ prime, right? And therefore we have P prime Q prime is less than or equal to P prime B plus BQ prime. which is less than or equal to P prime B plus BC plus Q prime C, right? Can you follow me? And we could also make use of the triangle inequality in triangle P prime A Q prime. In that triangle, we have P prime Q prime is less than P prime A plus A Q prime. So we could apply the first inequality here to inequality 2. This gives us 2P prime Q prime must be less than PA prime plus AQ prime plus Q prime C plus BC plus P prime B, right? And the right side equals AB plus AC plus BC. You see that? Because we know P prime A plus P prime B is AB, right? And this is our BC, and AQ prime plus Q prime C is AC. Therefore, the right side is actually AB plus AC plus BC. Therefore, we have proved P prime Q prime. Well, actually, PQ. PQ, first of all, is less than or equal to P prime Q prime. Also, P prime Q prime is less than 1/2 of the parameter of ABC, right? Which is a desired conclusion. Okay, have a look at the solution here. Let me know if you have any questions, okay? Alright, so that's basically the questions in the homework of topic 10.